Every chemical reaction must overcome an energy barrier before it can proceed. This barrier, known as activation energy, determines how fast a reaction occurs and whether it is feasible at a given temperature. At the top of this barrier lies a fleeting molecular configuration called the transition state, a high-energy species that exists for only a fraction of a picosecond. Understanding energy diagrams, activation energy, and transition states is essential for predicting reaction rates, designing catalysts, and controlling chemical reactivity. In this presentation, we will explore reaction coordinate diagrams, the Arrhenius equation, transition state theory, catalytic mechanisms, and work through quizzes and detailed problem solutions. By the end, you will be able to read any energy diagram and understand exactly what controls a reaction's speed and pathway. A reaction coordinate diagram plots the potential energy of a chemical system against the progress of the reaction. The horizontal axis, called the reaction coordinate, represents the progress from reactants to products. The vertical axis shows the potential energy of the system. For an exothermic reaction, the products sit at a lower energy level than the reactants. For an endothermic reaction, the products are higher in energy. In both cases, the pathway passes through a peak, the transition state. The height of this peak above the reactants is the activation energy IA. The overall energy change from reactants to products is the enthalpy change delta H. Every point along the curve corresponds to a specific arrangement of atoms. At the transition state, bonds are partially broken and partially formed, an unstable, high-energy configuration that determines the reaction rate. Transition state theory, also called activated complex theory, describes the fleeting species at the peak of the energy barrier. The transition state is not an intermediate. It is a transient molecular configuration where old bonds are partially broken and new bonds are partially formed. It exists for roughly 10 to the minus 15 seconds, the timescale of a single bond vibration. Unlike an intermediate, which is a stable species at an energy minimum, the transition state sits at a saddle point on the potential energy surface, a maximum along the reaction coordinate, but a minimum along all other coordinates. The Hammond postulate states that for exothermic reactions, the transition state resembles the reactants more closely, while for endothermic reactions, it resembles the products. This structural insight helps chemists understand which bonds are most affected during the rate-determining step. Activation energy. IA is the minimum energy that colliding molecules must possess for a reaction to occur. The Arrhenius equation relates the rate constant K to EA. K equals A times e to the negative EA over RT. Here, A is the frequency factor accounting for collision frequency and orientation. R is the gas constant 8.314 joules per mole Kelvin, and T is temperature in Kelvin. A reaction with EA equal to 50 kilojoules per mole proceeds about 1,000,000 times faster than one with EA equal to 150 kilojoules per mole at room temperature. The exponential dependence means even small changes in EA dramatically affect reaction rates. The Arrhenius equation can be linearized. The natural log of K equals the natural log of A minus EA over R times 1 over T. Plotting natural log of K versus 1 over T gives a straight line with slope negative EA over R. This is how chemists experimentally determine activation energies. A catalyst speeds up a reaction by providing an alternative pathway with a lower activation energy. Crucially, catalysts are not consumed. They are regenerated at the end of the reaction. A catalyst does not change the thermodynamics delta H of a reaction. It only affects the kinetics. Consider the decomposition of hydrogen peroxide. 2H2O2 yields 2H2O plus O2. Without a catalyst, EA is about 75 kilojoules per mole. With the enzyme catalase, EA drops to about 8 kilojoules per mole, a nearly tenfold reduction that makes the reaction proceed 10 to the 11th times faster. Catalysts work by stabilizing the transition state, making it easier for the system to reach the activated complex. In heterogeneous catalysis, the reactant adsorbs onto a solid surface, weakening its bonds. In homogeneous catalysis, the catalyst participates directly in the reaction mechanism. Enzymes are biological catalysts with exquisite specificity for their substrates. Not every collision leads to a reaction, even if the colliding molecules have sufficient energy. The frequency factor A in the Arrhenius equation accounts for two critical factors: the collision frequency Z and the steric factor P, which describes the fraction of collisions with the correct orientation. A equals P times Z. The steric factor P ranges from near 1 for simple atoms to 10 to the minus 6 or smaller for large complex molecules. For example, the reaction between NO and ozone is highly sensitive to orientation because the nitrogen atom must approach the ozone molecule at a specific angle. In transition state theory, the frequency factor also incorporates the entropy of activation, how ordered the transition state is compared to the reactants. A highly ordered transition state with a large negative delta S double dagger means a smaller a factor and a slower reaction, even if IA is modest. Let us integrate everything by comparing energy diagrams for different scenarios. An uncatalyzed reaction has a high activation barrier. Few molecules have sufficient energy to cross it, so the reaction is slow. A catalyzed reaction follows a lower energy pathway. The barrier shrinks, and many more molecules can react per second. An exothermic reaction with a high IA may be thermodynamically favorable, but kinetically slow. This is why diamond does not rapidly turn into graphite despite being energetically favored. By contrast, an exothermic reaction with low IA proceeds explosively, like the combustion of hydrogen. Understanding the relationship between thermodynamics, delta H, and kinetics, IA, is one of the most powerful concepts in chemistry. The transition state theory and Arrhenius framework allow us to design conditions and catalysts that give us control over both the rate and the outcome of chemical reactions. Quiz question 1. What does the activation energy IA represent on a reaction coordinate diagram? Option A, the energy difference between reactants and products. Option B, the energy difference between reactants and the transition state. Option C, the energy of the products minus the energy of the reactants. Option D, the total energy released as heat. Take your time to think about the answer. Quiz question 2. Which of the following best describes the transition state? Option A, a stable intermediate that can be isolated. Option B, a transient species at an energy minimum. Option C, a high-energy species with partially formed bonds. Option D, the final product of the reaction. Quiz question 3. According to the Arrhenius equation, K equals AE to the negative EA over RT, doubling the activation energy at constant temperature will do what? Option A, double the rate constant K. Option B, halve the rate constant K. Option C, decrease K by a very large factor. Option D, have no effect on K. Quiz question 4. What effect does a catalyst have on a chemical reaction? Option A, it increases delta H of the reaction. Option B, it makes endothermic reactions exothermic. Option C, it provides an alternative pathway with lower EA. Option D, it is consumed and must be continuously added. Quiz question 5. What does the Hammond postulate predict about the transition state of an exothermic reaction? Option A, it resembles the products more than the reactants. Option B, it resembles the reactants more than the products. Option C, it has exactly half the energy of the products. Option D, it is equally similar to reactants and products. Problem 1. Arrhenius calculation. A reaction has a rate constant of 0.0250 per second at 300 Kelvin and 0.195 per second at 320 Kelvin. Calculate the activation energy EA in kilojoules per mole. R equals 8.314 joules per mole Kelvin. We start with the 2-point Arrhenius equation. The natural log of K2 over K1 equals EA over R times 1 over T1 minus 1 over T2. Substituting the values gives natural log of 0.195 over 0.0250 equals EA over 8.314 times 1 over 300 minus 1 over 320. Compute the left side. Natural log of 7.80 equals 2.054. Compute the temperature term. 1 over 300 minus 1 over 320 equals 20 over 96,000, which is 2.083 times 10 to the minus 4 per Kelvin. Now solve for EA. 2.054 equals EA over 8.314 times 2.083 times 10 to the minus 4. So EA equals 2.054 times 8.314 divided by 2.083 times 10 to the minus 4, which is 82,000 joules per mole. Converting to kilojoules per mole gives 82 kilojoules per mole. Problem 2. Arrhenius factor comparison. Reaction A has EA equal to 40 kilojoules per mole. Reaction B has EA equal to 80 kilojoules per mole. How many times faster is reaction A than reaction B at 298 Kelvin? Assume the frequency factor A is the same. R equals 8.314 joules per mole Kelvin. The ratio of rate constants is Ka over Kb equals e to the Eb minus Ea over Rt. Eb minus Ea equals 80,000 minus 40,000 equals 40,000 joules per mole. RT equals 8.314 times 298 equals 2,478 joules per mole. The exponent is 40,000 over 2,478 equals 16.14. E to the 16.14 equals 1.02 times 10 to the 7th. So reaction A is about 10 million times faster than B. Doubling EA reduces the rate by a factor of 10 million, demonstrating the exponential power of the activation barrier. Problem 3. Eyring equation. Using the Eyring equation, calculate the rate constant at 298 Kelvin for a reaction with delta H double dagger equal to 50 kilojoules per mole and delta S double dagger equal to negative 80 joules per mole Kelvin. Kb equals 1.381 times 10 to the minus 23 joules per Kelvin. H equals 6.626 times 10 to the minus 34 joule seconds. The Eyring equation is K equals KBT over H times e to the delta S double dagger over R times e to the negative delta H double dagger over RT. First, calculate the pre-exponential frequency factor. KBT over H equals 1.381 times 10 to the minus 23 times 298 divided by 6.626 times 10 to the minus 34, giving 6.21 times 10 to the 12 per second. Next, the entropic factor. Delta S double dagger over R equals negative 80 over 8.314 equals negative 9.62. E to the negative 9.62 equals 6.63 times 10 to the minus 5. Now the enthalpic factor. Delta H double dagger over RT equals 50,000 over 2,478 equals 20.18. E to the negative 20.18 equals 1.75 times 10 to the minus 9. Multiply all factors. K equals 6.21 times 10 to the 12 times 6.63 times 10 to the minus 5 times 1.75 times 10 to the minus 9, giving 0.72 per second. The large negative delta S double dagger significantly reduces the rate. Problem 4. Temperature dependence. A reaction with EA equal to 65 kilojoules per mole has K equal to 0.045 per second at 295 Kelvin. At what temperature will K triple? R equals 8.314 joules per mole Kelvin. Use the 2-point Arrhenius equation. K2 is 3 times K1, so natural log of 3 equals 1.099. EA equals 65,000 joules per mole. T1 equals 295 Kelvin. Substituting, 1.099 equals 65,000 over 8.314 times 1 over 295 minus 1 over T2. 1.099 divided by 7,819 equals 1.406 times 10 to the minus 4. 1 over T2 equals 1 over 295 minus 1.406 times 10 to the minus 4, which gives 3.249 times 10 to the minus 3. So T2 equals 307.8 Kelvin. Only a 13 Kelvin increase is needed to triple the rate. Problem 5. Energy diagram analysis. For a reaction, the reactant energy is 0 kilojoules per mole. The transition state is at plus 95 kilojoules per mole, and the product energy is negative 42 kilojoules per mole. Calculate Part A, the activation energy, Part B, delta H, and Part C, the reverse activation energy. For Part A, IA equals energy of transition state minus energy of reactants equals 95 minus 0 equals 95 kilojoules per mole. For Part B, delta H equals energy of products minus energy of reactants equals negative 42 minus 0 equals negative 42 kilojoules per mole. The negative delta H means the reaction is exothermic. For Part C, reverse IA equals energy of transition state minus energy of products equals 95 minus negative 42, which is 95 plus 42 equals 137 kilojoules per mole. The reverse reaction has a higher barrier because it must climb from the low energy products back over the transition state. Let us consolidate everything we have learned about energy diagrams, activation energy, and transition states. The activation energy, IA, is the energy barrier that reactants must overcome to form products. It is the height of the energy hill from reactants to the transition state. The transition state is a fleeting, high-energy species at the peak of the energy diagram, where bonds are partially broken and partially formed. The Arrhenius equation, K equals AE to the negative EA over RT, mathematically connects EA to the rate constant, showing that even small changes in EA produce enormous changes in reaction rates. Catalysts lower EA by stabilizing the transition state, dramatically accelerating reactions without being consumed. The Eyring equation from transition state theory separates the enthalpic and entropic contributions to the barrier. Experimentally, we determine EA from rate measurements at different temperatures using the linearized Arrhenius plot. Understanding these concepts gives chemists the power to control the speed and pathway of chemical reactions, from the catalytic converters in cars to the enzymes that sustain life.